Okay, so welcome everyone. So the first speaker of this session is Professor Ganesh.
Good evening. First, let me thank the organizing committee for the invitation. I think it's very nice to see people who are working in a close area, something like this, 1.5 days to interact with them. So thank you very much for the committee for inviting me here. So as you see here, the title is actually very generic. I don't have any specific title. So the reason being that I just wanted to go through the work, what we have done in the last 5-6 years, and then how much we have contributed to this particular title. So that's the reason why I kept this title is very generic. So as you see here, we are more working on this supramolecular gel systems. So before we go into that, what are the other areas we are more focusing on this? So these collagen mimicking peptides, we try to mimic the collagen with the smaller peptides. As you know that collagen is a biomolecular system. And also we are working on this peptide-based surfactants. Recently we have some attractive, interesting data on that. And also we work on this amyloid fibrils and its inhibitions. So all of them actually centered around this molecular self-assembly process. So that's where actually we are more focusing on that. So let's get into the topic. So I think maybe some of them covered this particular the polymerization. So we all know that the polymer is a high molecular weight compounds which comes from the monomers, where they are actually the monomers are linked through the covalent bond. Right? So if you look at that, if somebody thinks about that, I want to mimic this polymer, but without having this covalent bond. So earlier, actually, maybe a couple of decades back, people were wondering that how it is possible. But nature actually inspires us that, there is a possibility for making such a kind of a polymers without having the covalent bond. If you look at the cell membrane, so this is actually made up of small lipid molecules. The lipid molecules is very low molecular weight. Right? But it makes that such a big actually structures. If you carefully look at it, there is no covalent bond between this. So how this nature makes this particular lipid molecules assemble into the bilayer is actually telling us that there is a possibility you can still make a bigger molecules or supramolecular system using a small molecules. Not only that, even we know that the DNA is a double helix. If you see that there is an interaction between this single strand between the single strands or actually the hydrogen bonding, right? So this also actually tells us that by using this molecular self-assembly process, you can build this molecule. Not only that, there are proteins which are actually functional only if there is a dimer or trimer or tetramer. I think the last talk was actually talking about this dimer, tetramer, etc. Right? So basically, what nature tells us that if you have a single molecule, which is not a functional one, but when it is assembled here, it can convert that from the functional, non-functional to the functional one. Right? So keeping this in mind, so when the molecules, the small molecules get assembled, right? So it can form like a polymer-like chain, right? So when it is in the aqueous solution or any organic solvents or something, so because of this assembly, the whole hydrophobicity of the molecules is getting increased. As a result, this will get into the get into the phase separation. As a result, it's come out from the solution. So in some cases, what happens? These supramolecular systems actually forms a polymer-like system, and then it immobilize the water molecules. So that is actually ended up with the gel. So gel is nothing but the three-dimensional structure, three-dimensional molecules, which has a viscoelastic nature. So generally the gels actually, if you look at this, many of the people know that it comes from the polymer, which are actually covalently linked. But there are other categories where the physical castings, what I am talking about here is, we can be classified into 3 categories. When it is immobilize the water molecules, we call it as a hydrogel. When it mobilizes the organic solvents, we call it as a organogel. But there is an intermediate class where we call it as the ambidextrous gelator. That means it's a single gelator which can gelate water molecules as well as the organic solvents. There are n number of gelators who are there for hydrogels. There is n number of gelators for organogels, whereas very few numbers are available for the ambidextrous gelators. The reason is there is no kind of a molecular structure and the gelation correlation. It is very difficult to predict a molecule whether it forms a gel or not. So that's actually the basic understanding is actually missing now. So why we should worry about this supramolecular, why we are interested about this supramolecular system? If you look at that, there are actually several fields actually now these supramolecular gel systems are actually used. You can see that the tissue engineering is one of the the area where this gel system is actually, because it is extracellular matrix is actually mimicked with this three-dimensional gel systems. So not only that, even for the drug delivery, it is actually now people are considering that. And then also there are several other, the areas where the supramolecular gel systems are actually used. Particularly when you look at these hydrogels, these are actually, you can find that, all these areas are actually, very important, and then very productive way you can get these things. So similarly, these organogels also having this lot of other applications, right? So what is our actually when you look at this, the academic industry. So right, so the academy has a different kind of a view on the supramolecular gel systems, whereas the industry is also interested, but they have different kind of systems. But why industry is now looking at this supramolecular gel systems? Because this, as I said in the previous slide, this supramolecular gel system having wide applications, still the area is getting increased. Wherever possible, these gel systems are actually, even the solar cell also they are trying to implement this kind of hydrogel systems. So, and it's also cost effective, and then also it's biocompatible, because if you, depending on the molecular system which you are choosing, this will be a compatible and then non-toxic, eco-friendly, easy synthesis, and then wide applications. So if you look at the academic perspective, what we look at here is a fundamental understanding. How these small molecules form the gel. So how these polymers are built, what are the forces actually is driving that. So why certain molecules only forms the gel, not all the molecules. So then also we are interested to create a novel gelators depending on the requirement or maybe any target applications. So one of the important actually the advantage of the supramolecular gels, I will be talking about the next slide, is the stimuli responsive. So if you have any kind of a stimuli like the pH or the temperature or the salt or any metal, that will be very sensitive. So using that stimuli responsive nature, this supramolecular gel systems actually very useful. So and then there are a lot of extending applications. If you look at this, the years, you see that it's not like a very drastic change in this supramolecular systems area. Right. So why supramolecules? We all have these polymer systems, but there are several advantages when you think about these supramolecular gels. So the first one is the chemical modification, because it requires very small molecules. You don't know, you're not going to spend a lot of time for the synthesis and then making this. So the second one is the critical gelation concentrations. Generally, you need a lot of samples for these polymer-based gel systems, whereas here you can have a very low concentration sample, which can immobilize large number of water molecules or maybe any kind of organic solvent something. Then the very interesting thing, what I told you in the last slide, is the stimuli responsive. Stimuli responsive, as I said that, the pH, temperature, metal, anything you can do it. Depending on your requirement, you can tune this. Then the gelation kinetics. So convenient for the tuning. One of the important, properties of this supramolecular gel is depending on your requirement. Let's say like I need very high stiffness gel. I don't need high stiffness, I need only very weak gel. So all these can be tuned by just tuning these kinetics. Then similarly for this chemical crosslinks, there is no chemical crosslink is required here. So if you look at any polymer system where they use any bifunctional molecules or something to increase the polymeric length, so that can immobilize the solvents. But here there is no chemical crosslinks is required, because whatever the molecule you are choosing, that is more than sufficient for making the polymer-like structures. And then it's very dynamic. If you look at that, once you break the gel, most of the gels comes back. So that's a self-healing kind of a things. That is actually the advantage for this. So there are so many advantages with this supramolecular gels. Right. So we are interested in this supramolecular gel systems. When we look at the literature, there are several small molecules have been already proposed. Right. So in this, actually, we are interested in amino acids and then peptide-based systems. Peptide is actually very short peptide-based systems. So the reason being that, so as you all know that amino acids are actually the building blocks of the protein. So there will be not be any toxic problem, and then it's also highly biocompatible and also easy to functionalize, because it has two functional groups. One is a carboxylic acid, the other one is amine group. So you can easily functionalize this amino acid. Similarly, the peptides, you can see this is biocompatible. and there is a low immunogenicity, and then high target specificity and selectivity. That means the peptide sequence what you are choosing, I mean, if it wanted to target some places, you can tune the sequence, specifically. Then it is a low accumulation in tissues because it is undergoes the proteolytic cleavage. It will not stay for a long time, and also easy to functionalize, similar to the amino acids. Right. So now, what is the question we are going to address?
How do you tune the time constant for recovery? In the sense, if a bond breaks, how swiftly you can reset the self-healing part of the system?
Right.
So how do you control the self-healing time? You control that.
You won't control the self-healing time, but you can use the temperature. So let's say you break the you break the gel, and then you probably increase the temperature. So then the self-healing.
But not by the linkers that we use, kind of linkers.
No, no. So here there is no linker actually. The molecule itself will actually assemble. So we are, as I said, that there is no cross linkers here we have used. So we are actually we are just building like using these intermolecular interactions like hydrogen bonding, aromatic pi-pi interactions. So like that, you build this monomers into this thing. So there is no cross linkers required for that. So what we are going to address? So what is the question we are going to address? So there are several actually amino acid based systems are available. If you look at this slide, there are almost 22 amino acids are there, but the amino acids which forms the gel is containing only, is having only 6 amino acids, right? So all of them is actually functionalized with the fluoronyl methoxycarbonyl. So this particular aromatic system is facilitating the pi-pi stacking interactions. But despite that, despite 22 amino acids, only few of them is actually showing the gelation properties. So the remaining them are not showing the gelation properties. Why? So what could be the reason? Right? So that's what we are going to address. As you know that this is a self-assembly system which is actually mainly driving the force with the hydrogen bonding, aromatic and other things. So first what we wanted to focus is to look at the hydrophobicity. So the aromatic, the amino acid side chain you see, polar, non-polar, ionic, all these actually the variety of amino acids are there. So what we started to look at it, how this hydrophobicity of the side chain is actually influencing the self-assembly property and thereby the gelation. So the first one is what you're looking at as the methionine amino acid, which is functionalized with the F-mark. There actually we slightly change the sulfur to CH2. So this is the F-mark narleucine, right? So and then we oxidize this sulfur to the sulfur dioxide. The reason is this is actually electronegative atom. This is more actually non-polar nature than this one. When we oxidize this sulfur dioxide, this is actually more hydrophilic than this one. So we have two systems. One is more hydrophobic, and then the mid one, and then the more hydrophilic. Then this one system is actually we have chosen in order to look at that whether this fluoronyl group is required for the self-assembly formation. And then when you look at this, both of them are aromatic. So in case if this forms the gel, then we need to look at that whether the aromatic system is required. So for that we have chosen the tertiary butyl group. Right? So the results are very interesting. So this F-mark methionine has actually formed the gel. So this is basically the vial inversion test. So visually you can check whether the solution forms the gel or not. Right? So when you invert the vial, so the gel will stay on the top of this vial. Right? So if you just change this small electronegative atom to the hydrophobic system, you see that there is no gelation. Right? So when you oxidize this, it still forms the gel. Right? So whereas if you replace this fluoronyl group to the benzene, so it is not forming the gel. So it's a liquid. So similarly for the tertiary. So what this tells us here is, if you change a slight change in the hydrophobicity of the side chain, you can convert the gelator to a non-gelator, or you can convert. Yeah, I will come to that. I'll come to that. Yeah. Right. So now, whatever the concentration you are looking at here is the minimum gelation concentration. So that is the minimum gelation concentration is required for the formation of the gel. If you look at this, it's only 0.8 millimole. If you look at this, it's 8 millimole. So what happens here basically? We are altering the balance between this aromatic system with the hydrophobic system. So the balance here is different, right? So that indicates that you need a more concentration to make the gel. So by looking at this, we understand that any change or even a minor change in the hydrophobic system in the side chain will lead to different kind of a response. So that is actually the pictorial representation, but experimentally we need to confirm that whether this has a viscoelastic nature. So we did this, rheological studies. As you see here, this is amplitude. We typically use this as a starting measurement. So where the G prime, which is actually the storage modulus, the G double prime is the loss modulus. So for a gel system, G prime is actually always greater than the G double prime. So that's what we see here, this amplitude sweep. And then we also check the time sweep. So how long it takes to form the gel. So when you look at here, this takes like almost 30 minutes for this system to form the gel, right? And also we looked at this frequency sweep, which is actually another parameters to look at, is there any dependency in the frequency for the gel to display. If you look at this, this graph is actually the step strain sweep. This is basically for the thixotropic nature, right? So once you break the gel, whether it comes back or it's a self-healing property. So this is an experiment we do. So basically you apply a very small amount of the stress in the beginning. So where G prime is greater than the G double prime. So when you increase the stress to 100%, so you can see that the reverse in the G prime and the G double prime. So when you release the strain, it comes back to the norm. So the time what we give here is 2 minutes. So you keep this gel under the high stress, it converts it into liquid form. As soon as you release the stress, it comes back. So like this we do like a 2 or 3 cycles. We see that whether it comes back this property. So that's how we confirm this regelation properties. So all we are looking at is actually the molecules, right? But once you put it in the, the liquid system, it converts into the gel form. So we confirm that whether the self-assembly is happening in the system. So this is atomic force microscope. What you are seeing here is actually lengthy fibers. It is similar to what we see in the polymers, right? So this is basically the responsible for immobilization of the solvent molecules, because the solvents have the capillary action with these fibers. So that's thereby the solvents are actually getting immobilized. So we do a lot of characterizations to understand how these molecules are self-assembling into the fibrils. So what you see here in the top is the fluorescence spectroscopy. So there you can see that this 312 is actually corresponding to the particular monomer peak. Once this self-assembly occurs, then you can see the red shift that indicates that there is a F-mark group which is actually getting pi-pi stacking. So similarly, we do this circular dichroism, which basically is an induced circular dichroism. If you have a single monomer, you don't see anything, any response, because the pi system is getting assembled. So you get the induced circular dichroism. This is a peak which is corresponding to this particular fluorinyl group. And also we check, is there any hydrogen bonding, because in the system you see that there's a amide group here, and then also the COOH group here. So is there any driving force from this hydrogen bonding? So that's information you get from the FTIR. You can see here this is 1716, which is corresponding to this particular carbonyl group. Once you have this gel, you can see it is shifting to 1618 and 9 centimeters inverse, which is telling us that there is hydrogen bonding between this. So based on this experimental, and also we do this powder XRD, which confirms that this pi-pi stacking is there. So by looking at this 0.33 nanometers for the aromatic stacking. So we believe that, based on this experimental data, this could be the, arrangements of these molecules, which leads to the entanglement of the fibers. Right. So the next is actually what we wanted to focus is, we have focused the hydrophobicity. Yes, it is a very important for this self-assembling system. So next we wanted to focus how this aromaticity is very important. So for any protein, if they wanted to understand, so they will focus on, depending on the function or something like a phenyl groups or maybe the aromatic amino acids, by replacing it with the aliphatic amino acids to understand how this particular amino acid is responsible for that. But what we want to do here, we don't want to change this system completely to understand the aromatic system, because when you change this, then totally you are changing the amino acids, right? So you can't get really the effect of the aromatic aromaticity for the gelation purpose. So what we did was we simply removed this aromaticity from this. So we have the cyclohexyl ring here, right? So let's see that what's the effect. So what you see here is actually the F-mark phenylalanine, which is actually well-known gelator, which forms. So when you replace this particular benzene with the cyclohexyl ring, so you see that, it forms the gel. But the interesting observation here is within 20 minutes, it actually converted into the liquid form, right? So accidentally, the students actually heated this one, because she was worried that, she was not able to get the gel. So she heated this one, and then again she got the gel. But what happened, overnight, it again turns to the gel, solution form. So again she did that, okay, we'll just heat it one more time, and then you see that over the 2 months this becomes stable. So what could be this, what is making this is a big difference when you are just shifting, one cycle to the other cycle to the other cycle, right? So what we did is actually we looked at these electron microscopic images for the corresponding solutions here. You see here, the first time when you are making this, it's not forming a very entangled fibers, which is required for the immobilization of the solvent molecules. But whereas when you are heating the second time, right, there is some kind of a fibers is started forming. But whereas in the third time, you can see the highly entangled fibers. That's why this gel is actually more stable, right? So the heating actually is very important. And then which also corroborated with our AFM microscopic images. So what is the effect we are getting by changing this aromaticity, right? So FMOC phenane also forms the gel, but after 2-3 cycles, this also forms the gel. So that means aromaticity is not required, right? So that's the question we asked. Then we looked at this thermal stability. So this is actually again the vial inversion. Sorry, the image is not very clear here. This is a vial inversion test. You increase the temperature, right? And then you can see that at 65 degrees, this FMOC phenylalanine which melts to the liquid. Whereas when you look at this FMOC CHA, which melts at 50 degrees. So there is a 15 degrees difference between this aromatic characters when you have the difference, right? So that indicates that people, when they are looking at this aromatic benzene ring, aromatic system, so that basically helps to increase the stability of the system rather than it is not, giving much importance for the formation of the gel, right? That's what actually the information we get. So the aromaticity of the phenyl to increase the thermal stability of the supramolecular gel systems, right? So we looked at the hydrophobicity. Very small change in the hydrophobicity will influence this hydrogel system, and also we looked at the importance of the aromaticity. Then now we wanted to look at the significance of the FMOC group, right? So there are so many systems which has been reported with this FMOC groups. They have said that is one of the highly promoting system. If you are looking for any hydrogel small molecules to convert into the gelator, you can use this. But we learned from the previous, the first slide of this working thing, even though the FMOC group is protected with all the amino acids, only few amino acids are forming the gel. So that means it is extending, it is supporting for some time, to some extent, but not for all the time. So what we did was, we actually thought of that, why can't we have one more FMOC group in the system, right? So for that, we have chosen this lysine because it has the two functional groups, two amino groups, which is easy to functionalize. So you can build this structures like one FMOC group in this amino terminal, the other one is the side chain amino group. So by incorporating this, actually the fluorinyl group, we are also introducing the additional hydrogen bonding, right? So what we get from this? So we are introducing the additional pi system, also introducing this additional hydrogen bonding. So the expectation is like this. So since we have a large number of aromatic system now and also the hydrogen bonding systems, we expect that this particular gelator may gelate both water molecules as well as the organic solvents, right? So and also we know that, as I mentioned before, these FMOC amino acids are all actually showing only the hydrogels. There is no organogels for that. So, and also the ambidextrous gels are very, very rare. So the idea of putting this is actually increasing this pi systems as well as the hydrogen bonding, which may help us to discover or maybe find a new ambidextrous gelators from the amino acids, right? So, but just you having this may not help us that whether this actually playing an important role for in case if it turns out to be ambidextrous gelator. So for that, we built another 3 molecules. So just we replace this FMOC with this phenyl ring, and then this tertiary butyl, and then without this. This is the FMOC lysine, right? So when you look at the response for this particular modified system, you see that very interestingly, as we expected, that this forms a wide, hydrogel in a wide range of a pH. Not only that, you can see that some of the organogels is also, organogels formed for some of the selected organic solvents, right? So that means by introducing this kind of additional pi system in a gelator, you can basically convert them from a normal gelator to a ambidextrous gelators. So if you look at this this and this and this, you can see this FMOC, the block, actually this is a 1, which doesn't have any kind of, this is a liquid which is actually in the bottom of this. There is no gelation for this. So that indicates that this is very, very important for that particular ambidextrous gelator, right? So if you look at this one, so this forms the gel at pH 6, whereas pH 7.4 it's not formed. So, and also this is a very weak gel, I mean, based on the rheologist data. So this helps to some extent, but it is not, I mean, very good in all the pH range. When you look at this FMOC lysine alone, it doesn't have any pH, right? So by substituting the FMOC group in a system where you have other FMOC group, which basically converts that into ambidextrous gelators, right? I mean, we confirmed that with the rheology data. What you see here is the angular frequency sweep. So you can see that it's a pH dependent. So the pH 6 has the more viscoelastic nature because the G prime value is very higher than the 7.4 and then this 8.8. Interestingly, I think this pH 6 is showed as a complete, I mean, almost 95% of the recovery of the gel, whereas the other two pHs is not as good as the pH 6.4. So that indicates that this thixotropy is actually the pH dependent for this system. Right, I mean, these are the microscopic images. You can see the fibrous nature for all the pHs. What we have got the gel, right? So, but each of them has kind of different kind of I mean, morphologies. One of them is skin-like a morphology here, and then this is actually fibrous-like, I mean, scaffold-like morphology here. So here is a non-porous, and then some crystalline natures is also, I mean, observed in this case. So the another important property when we go for the supramolecular gel system is to look at the temperature, right? So you imagine that, I mean, we are using these water molecules for immobilizing this, and then if you take any polymer system, you can heat up to 100 degrees or 150 degrees or 200 degrees something. But you look at this, I mean, at pH 6, even at 100 degrees, I mean 90 degrees or something, 95 degrees, 100 degrees, this gel is actually, you know, still stable. So that means the interaction between these water molecules and this gelator is very strong, so which holds this at pH 6 is nearly high temperature. But again, this the temperature, I mean the T gel is actually depends on the pH. It decreases with increasing the pH. Okay. So the reason is at higher pH, this particular molecule actually there is a COH group here. So this at high pH, this will be a COO minus. So which will be actually a repelling nature, whereas when you decrease the pH, this negative charge is getting converted into the neutral, that's a COOH form. So that's why this pH dependent effect we observe for that, right? So I'm not going into this, I mean, characterization as I discussed this before. So going back, going to the possibility of the molecular arrangement, right? So there are two possibilities. One is the parallel arrangement, the other one is the anti-parallel arrangement. So because this is not the symmetric molecule, because the COH is somewhere here on the left side. So what we proposed was either this A, the fluorinyl moiety has been stacking with this B and B, and then A and then B, and the head to head or A to tail. So this can be in a parallel orientation or this can be in anti-parallel orientation, but unfortunately it's very difficult to just find out what kind of a structure is actually present in the system. Right, this is actually the electron microscopic image for the organogel. Actually similar to the hydrogel, this also forms these fibrous kind of natures. Right, so now coming to the other the topic. We know that, I mean, this addition of this FMOC group is converted that small, the gelator from the hydrogelator to the ambidextrous gelator. Now we thought that, okay, we can just, instead of just doing some replacement, why can't we go with some functional moiety, right? So which can be used for some specific applications. So now we replaced this particular system with the pyrene. So this pyrene is very well known dye and has been used for many, many applications. And then this is a biotin, which is biologically is very important molecules. And then this biotin is bioavailability is very less because it's a poorly soluble in water system. So if anybody gets this, a biotin in a gel form, that will be more applications that can be fine. So here is actually the importance of the pyrene and this biotin. So as I said, this is a precursor for many of the dyes. And also these fluorescent spectroscopy. This can be used as a staining agent. And also this can be used for the charge transfer because it's an electron rich system. For any charge system you can use it. Similarly for this biotin is actually necessary for the cell growth, and then also it assists the various metabolic reactions, and particularly this acting as a receptor ligand interactions with the avidin. and the cyclodextrin and other things. So based on the previous experience, if we get some kind of a gelation from these molecules, that will be more interesting to for several applications. So as you see here, this is a similar system as what the FMOC, di-FMOC system what I showed you. So the results we used is a TNF, trinitropulvene. Actually, this is an electron deficient molecule. So what the idea here is, this is the electron rich center we have. So once we have this electron diffusion center in the system, so whether this can convert, transfer the charge from this to this, right? So what you see here is the hydrogel, right? And then it also forms the organogel, right? So now if you add this acceptor here, so this turns into the brown. That is an indication for this charge transfer from this pyrene to this. Not only that, we also subjected that into the UV radiation. So you can see here, without this TNF, this shows the fluorescence, whereas when you add this actually the fluorescence is quenched, right? So that happens for this organogel system also. So the model what we propose here is, so basically if you don't have this TNF, this is a system, this arrangement, and then when you have this TNF here, so that's intercalating between this two pyrene system, therefore the charge is actually transferred from this pyrene to this TNF, right? Then the biotin part, actually we are lucky that we got the hydrogel here. So in the literature, very, very difficult to get, you can find this biotin based hydrogel systems. So very importantly at the physiological pH, we got this the gel, and then this is look at this electron microscope image which shows a nice fibrous structures, and then this viscoelasticity of this hydrogel was confirmed with this rheology experiments. And this is actually the model is proposed as similar to what we have done, what we proposed in the last slide. Right. So now we have done 3-4 systems, right? Similar systems. Now what we wanted to look at here is attempt to develop a correlation between the molecular structure gelator and the ambidextrous gelation. So far, it is very difficult if somebody gives you a molecule that if they ask you that whether this molecule forms the gel or not, it's very difficult to predict. To some extent you can say, but most of the time it is very difficult to say. We can say that the molecules can self-assemble, but whether it immobilizes the solvents to convert that into the gel, that is a question mark. We cannot predict. So, but here what we try to do here is whether we can get some correlation, structure correlation with the gelation system. So for that we kept the same the di-FMOC, but we replaced that lysine with the diaminopropionic acid. So the difference between the lysine and the diaminopropionic acid is here is only one CH2, there is a 3 CH2 in the lysine case. So basically to change this system, maintain this one. Right. So interestingly, I think this also forms these ambidextrous gels. You can see that from 4.9 to 9.1, it very nice gels actually forms, right? So also this forms the organogels, right? So once, after getting these results, we went back to the literature and then we pulled out, what are the ambidextrous gelators are, reported, right? And then just see that, is there any correlation between these gelator systems? So when you look at these, all these systems where you see this color, right? These are all aromatic systems. And then these are all actually the hydrophobic system, but it is actually, the alkyl chains are there. So now if you look at this, looks like this is something like a dumbbell system, right? So if you look at this, all these molecules, it can be aromatic or hydrophobic, except this system, you can find that this shows this dumbbell system. So what we propose here is, if you design a molecule with this this kind of dumbbell shape, and then with either both the side aromatic, or one side is aromatic or the other side is aliphatic, or the vice versa, with this some hydrogen bonding capacity in between this, and then one polar group, right? So that actually you can expect that it can act as the ambidextrous gelator. So this actually work was published in the on the cover page of this journal, right? So we quickly I'll just move to maybe I have another 5 minutes. 5 minutes, yeah. So I think most of you know that this amyloid system, which is actually basically comes from the protein, which is actually getting unfolded. This unfolded actually proteins is unstable and then becomes a beta sheet. The oligomers, which actually converted into the fibrils. Right. So these amyloid fibrils are responsible for many diseases, right? So what happens basically, once this fibril forms, this will get phase separation out in the solution, you get the precipitate kind of things, right? But what we wanted to here is, we want to convert this amyloid fibrils into the hydrogelator. Right? Why? Because this particular amyloid based peptides are having an inherent property of this self-assembling into the beta sheet structures. Right? So using that, actually whether we can convert them into the for the 3D hydrogels. So what we did was actually we have selected this NFGIL. This is coming from this highlight amyloid peptide fragment. Right? So we did actually the gelation test for this after adding this, conjugating with this FMOC group. Right? So the interesting thing here is this minimum gelation concentration. So any applications for the biological applications, we have to look at the concentration. Because the gel, if you have very high concentration, that itself will be toxic. So if any of the applications, we always look at this minimum gelation concentration. So any gelation which is less than 0.1% in this supramolecular gel field, we call it as a super gelator, because very difficult to get a minimum gelation concentration less than 0.1. Right? So interestingly, after conjugating this, actually this, to this peptide, it is actually forming the, minimum gelation concentration which is less than 0.1. So here in this case is a 0.08. Also it showed the pH dependency. So anything is actually above 6.5, it forms a nice gel into this. So we confirmed this with the rheology, right? So the important thing, what I wanted to point it out here is, generally the solution will convert to the gel. Here as also it happens, but as soon as you add the solvent to the system, but it immediately it shows the difference between the G prime and G double prime. So that indicates that addition of this particular peptide is having a faster, kinetics for the self-assembly that leads to the hydrogelations. So the fibrillars is confirmed with the electron microscope, and then we propose this actually the structure based on the biophysical characterizations. Right. So now we move to the other peptide. Right. So this is actually alpha cinnulin fragment. Right. So this is actually one of my PhD student. We're sitting here. For her PhD work, she started working on this system. Right. So this is a system. Entirely different sequence, but after conjugating this to this sequence, you see that this is 0.03. That is a 0.3 milligrams per ml. That's very interesting. That to see that you have conjugated only one FMOC group, that's aromatic system, which actually not only converting that into the hydrogelator, also it shows this minimum gelation is only 0.03. Right. So this actually made us to think. Go back and then look at this sequence. What is there any, because this is also a super gelator which is actually showing low minimum gelation concentration. This also does the same thing. Is there any commonality between these two sequences? Right? Although these amino acids are different, there's one amino acid which is similar here, which is actually next to the FMOC. So that is asparagine. Right? So you all know that now the supramolecular self-assembly is facilitated by various intermolecular forces. One of them is hydrogen bonding, right? So in this sequence, the common is asparagine, right? So we thought that, okay, there is maybe a triggering factor from the side chain CONH2, which is influencing this actually the gelation system. So what we did was, we replaced this particular asparagine residues with the different amino acids, right? Keeping in mind that phenylalanine is facilitating, and also completely removing the aromaticity. And then this is a glutamine, which is actually one CH2 is actually more than this asparagine. Right? When you look at the results, it's tabulated here, sorry, it's very small. Except this asparagine, the remaining are all actually 0.1, 0.2, and then 0.6. Right? So if you just change this particular amino acids, which is drastically changing the minimum gelation concentration. So that indicates that this is actually the asparagine is playing an important role for this one, right? And then we went back to this old sequence that the NFGL. There also we did this similar kind of experiment, and then you see that the remaining all of them is showing the very high minimum gelation concentration. So that indicates that the asparagine is actually a very, very important role in reducing this minimum gelation concentration. So now I just finished this with the questions to address with this particular part. So now knowing that, okay, this asparagine is playing an important role, is there any direct intermolecular hydrogen bonding between asparagine side chain, which is actually facilitating this gelator into a super gelator? Or if not, is there any hydrogen bonding between asparagine side chain and the water molecules? And then, is there any water mediated hydrogen bonding between asparagine side chain? So if not direct contact, is there any water-mediated hydrogen bonding between, which facilitates the self-assembly process? Is there any hydrogen bonding network between the difference between the asparagine and glutamine, because both of them is having the same CONH2, CONH2, but asparagine is actually the super gelator, but not the glutamine. So with this, I mean, questions, I mean, we went for this molecular dynamics, which is under the process. So with this, I stop here, and then thank you for your attention. If you have any question. Okay, so before that, I just wanted to thank the people. So we thank CLRA for allowing us to do this work. And then the first part of this amino acid work is actually carried out by my PhD student, Murli Mohan Reddy. And then the second part is actually the Jaini flora. And then the last peptide part is actually Anaga. And then we thank Abhijit for extensive help in characterizing these hydrogels for the rheology experiments. And they are all actually the student of Abhijit. Thank you all.
Yeah. So let's thank Professor Ganesh for a very interesting talk. We still have time for a few questions.
Very interesting talk. I just have two questions. Firstly, when you are heating the system or you're changing the pH, does the chemical structure remain intact? Is it prone to hydrolysis or so?
No, it's intact.
It remains intact.
It's
And
intact.
secondly, when you are changing the pH, you are using sodium hydroxide or traditional inorganic acids, right?
No, we change the buffer itself.
Buffer
So, I mean, you know, there is a different kind of a buffers for different pH range. So we select, I mean, based on our requirement. Let's say, for example, pH 4.5 or 5, we choose sodium acetate buffer. If something like a pH 7 or 8 or something, we use a sodium phosphate buffer. So that's how we
if you
choose.
use, I mean, what I meant to say is that whether if you use organic cation or anion, does that have any effect on the gelation?
Definitely it will have. It will have. Because metal ions are very sensitive. So it may have, but we have not tested it actually.
Any more questions? Okay, so let us thank Professor Ganesh again.
Thank you.
So our last speaker for this session is Hitesh. So he's going to talk about bridging induced coil to globule transitions in polymers.
Hello. So first of all, I would like to thank the organizer to giving me the opportunity to present my work here. So the title of my talk will be bridging induced coil to globule transition in polymers. So after like experimental and more technical talks, let's end the day with the more fundamental question, like how many ways like coil to globule transition can happen. So so we all know now what polymer is. A polymer is a large molecule made up of repeating units called monomers, and these monomers are connecting to each other through a covalent bond to form long chains. And there are various examples in our day-to-day life of polymers, in synthetic as well as biological. So I'm more interested into the conformation of a polymer chain, how a polymer chain can take different conformation. So before that, like what polymer conformation will be there in different solvent quality, is known that in good solvent condition, chain will be in the extended kind of form. What we call a good solvent condition is when the attraction between the monomer is less than the monomer-Crowder interaction, solvent attraction. We'll call that as a good solvent condition, that and the chain will be in the extended form. by the logic that the monomer wants to have more contact with the solvent. And on the other hand, the poor solvent condition will be the condition when the monomer attraction is high than the monomer solvent attraction, and the chain don't want to in contact with the solvent, and hence form a collapse kind of form that we also call globule, and extended kind of form is known as coil kind of structure. And these, in good solvent and poor solvent, these Rg, radius of gyration, follows a nice scaling behavior. Rg varies as n to the power 3 by 5, and within poor solvent, Rg varies n to the power 1 by 3, where n is the number of monomer in a single chain. And these 3 by 5 and 1 by 3 is valid in 3D. It's a dimensional dependence coefficient. And in general, R varies as n to the power nu. Nu is scaling exponent that can be used to find the regime in which polymer is in. It can be in good theta or poor solvent. Then, like, what are the common ways in which we can get a coil to globule transition? And the coil to globule transition is kind of relevant, as some of the speaker already told that they are biologically relevant forms, whether the chain is in the extended kind or the coil kind of structure or in the globule kind of structure. So we know that, as I explained, the solvent condition can play a role in achieving the coil to globule transition. If the solvent quality is good and we module it to a poor solvent condition, we will get extended to collapse kind of structure. Then there are coil non-solvency is one of the another way we can get coil to globule transition, where if a single polymer chain is miscible or in good solvent condition for type 1 solvent and individually for type 2 as well, the mixture of type 1 and type 2 can give rise to a poor solvent condition and will make the chain collapse. This phenomena is known as co-non-solvency. And then the same can be achieved through temperature mediated. Increasing the temperature or decreasing the temperature can also induce the coil to globule or globule to coil as well, depending on whether the chain display LCST or UCSEST, lower critical solution temperature or upper critical solution temperature. Same if we have a charged polymer, that can also showcase coil to globule transition if we merely increase the charge density on the each monomer or the backbone charge density. Then polymer doesn't found themselves in a single solvent condition. They generally found themselves in a very crowded environment. In a like biological context, in the a particular nucleus can have a various segment, which we can call them a crowder. Crowder is a very basic term we can use. It can be of different shapes, sizes, as well as can be macromolecule. So crowder is a very generic term, and so it's really important to study polymer chain in a crowded environment, right? So if we have a crowder in our system, they can have typically two types of interaction with the polymer chain. First is they can have a repulsive interaction with the polymer chain, and that gives rise to what known as depletion kind of effect, where when these crowder density is increased and above a threshold value of the density, we'll see a coil to globule kind of transition. And these like kind of crowder depleted from the surface of the polymer chain to gain the translational entropy, and this phenomenon is known as depletion effect. So here are the, like you can see, as the density is increased, they kind of depleted from the surface to make the chain collapse, right? So the other interaction a crowder can have with the polymer chain or monomer is attractive attraction. Typically, one would think that if the crowder have an attraction with the monomers, chain would like to be into the extended form, as the same logic I gave for the good solvent condition, that they want to be in the more contact with the crowder particle. But what it has been found that the chain collapses with the increasing the attraction between the polymer and the solvent particle or the crowder particle. The attraction, this attractive crowder shows some counterintuitive behavior. So so you can see here the chain was extended for less attraction, but as the attraction is increased, the chain is now forming a globule kind of structure. And what happened, the crowder particle is acting as a bridge or a glue between the distant monomer to induce the collapse behavior. So what is happening, the single crowder particle, the green one is showing here, is now kind of acting as a bridge or a glue between the distant monomer, you can say here. So single can act as a kind of bridge between the two distant monomer. So there are a few studies here to showcase this, that indeed as we increase the polymer and the solvent attraction or the polymer or the Crowder attraction, we see the chain is going from collapse to extended to collapse kind of behavior. For these are some of the studies. So hence there is another way of this C to G transition is through attractive Crowder, and we are calling that a bridging interaction. So what questions are we addressing? So the earlier studies I have shown is kind of not complete in the sense they have focused on a very restricted range of parameters. For example, some of the studies only restricted to a particular monomer attraction, or some to particular densities, and some particular like short chains and all. And also there was no report of collapse to collapse transition as well in the literature, and these collapse to collapse transition has not been conclusive thus far. And apart from these questions, we are also trying to find out the critical value of the attraction between the monomer and the Crowder, which give rise to the this transition. So we are constructing a phase diagram for the critical value of the transitions, right? So before the results, I'll show what model we use. So it's a very basic model we can use. So it's a bead spring model with a single chain surrounded by the Crowder particles. In the blue you can see, and the solvent we have taken as implicit, that the monomer interaction will tell us whether the solvent condition is good or bad, and every non-bonded particle interacts via Lg interaction given by this mathematical form, and every bonded like adjacent bonded particle is modeled by the harmonic bond by the classical Hooke's law. Then the phase diagram. So this was one of our aim. So we analyze for different interaction of the monomer attraction and the monomer Crowder attraction. We analyze the radius of gyration of the chain, and I'll explain the radius of gyration behavior with the different interactions. So if we take epsilon mm 0.1, that means weakly attractive monomer, that the chain was in the extended form when there is no Crowder around. So if you see here, if there is no Crowder, the red curve shows us that the chain is in the extended form. And as we increase epsilon mm, that means we are increasing the monomer attraction, that now the chain is going to good to poor kind of condition, and now the chain is going from extended to collapse kind of behavior, right? So it was obvious, but as we look at this red curve and we increase the epsilon mc, that means increasing the monomer Crowder attraction, we see that there is a nice decrease in the radius of gyration, and chain is going from a extended kind of structure to globule kind of structure, right? So from there we find the inflection point of each curve to find the critical value where this transition occur, and from there we made a phase diagram out of it. And this looks like something this. So we primarily determine three phases. First is extended phase, that this one due to weak intrapolymer attraction, and then as we go increase the epsilon mm, we see that we go to another phase, Ci phase, that is collapse phase due to the intrapolymer interaction. Here the Crowder is playing no role, it's totally governed by the monomer attraction. But one more phase we found another collapse phase, that is collapse phase due to the bridging interaction, and this occur for both in like Ci to Cb phase as well as extended to Cb phase, right? So there are some like, this is the E phase I am showing, that's in the presence of Crowder, it shows most extended. Here the Ci phase, you can see where there are very less number of Crowder which are around it, and in Cb phase you can see there are the collapse phase, and it's mostly the Crowders are playing part in making this transition happen, right? So even though both the collapse phases are same, we are saying that they are two different phases we are determining, Ci and Cb, because they are maybe collapse phase, but they're structurally quite different. You can see from here the black and the red curve shows that this is Ci phase, totally determined by the monomer attraction. We see there are no Crowder inside this. So this y-axis is density profile of the Crowders. So we can see the black curve is showing 0 up to a certain distance, and then becomes equal to the bulk density, showing there is no Crowder inside the globule. Where in the Cb phase we can see there are quite a huge number of Crowder which are sitting inside the globule, right? So they are quite, and from same can be interpreted from the G of R plot. We can see in the CI phase, the radial distribution function for monomer, we see a peak, first peak, that means there is a neighbor of a particular monomer is a neighbor, but the same peak is absent for the CB phase, GMM, you can see the blue curve, there is no first peak, that means, and in the GMC, that monomer Crowder radial distribution function, we see the peak is emerges where the peak is absent for GMM in the CB phase. That means now the monomer particle is kind of replaced by the Crowder particle inside the globule. So these, the point is that these two collapse phases are quite different structurally. Then what is the effect of density we look? So some of the earlier studies showed that there is from the collapse to collapse transition is directly happening. We also see in our case that this one, initially we work with this particular density very dilute system that, and we see that the red curve is going from one collapse CI phase to CB phase directly without any extended kind of structure. But some of the earlier studies as well, and our study shows that as we increase the density, we will see a intermediate extended phase as well. So it's not going directly to CI to CB phase, there is an intermediate extended phase as well. So we can conclude here in the sense that these transition like CI to CB or E to CB all are density dependent, strictly density dependent, they are not absolute transitions. Then naturally we ask again same question, what happens if the polymer is charged 1? Till now I have talked about the neutral polymer. What happens if the polymer is charged 1? We give charge to each monomer, and so charged polymer has like various examples in our day-to-day life as biological polymer as well as synthetic polymer. So in model we will change in the sense that we now put charges on each of the monomer with some negative charge, and then to neutralize the system we have counter ions of the different valencies z equal to 1, 2, 3, and again the other things are same, and like non-bonded particle will interact via Lj potential, and the charged one will interact via electrostatic potential, and the bonded will be again the same harmonic potential, right? So before putting Crowder in a charge system, what we know about charge system without Crowders? Like we have a polar-electrolyte chain and just counter ions around it. What we know about that? How that transition happen? So we know that it's been established now that a poly-electrolyte is a name of charged polymer, undergoes a cold to globule transition as the charge density on the chain backbone is increased above a threshold, right? So that means if we have a charges on chain backbone, and if we modulate the charging on each monomer, there is a particular value AC of the charge density above which the chain will go from extended to collapse kind of structure, right? So there are few studies which are like these are the studies which shows what is the value of AC to find for the different. So this AC value will depend on the valency of the counter ion as well, and the various other parameters. So and this kind of collapse can be understood by the phenomena called Manning condensation. And what happens that the counter ions come and condense on the chain backbone to neutralize the system and make the chain collapse. There are few studies more recently going on with the dipole-dipole interaction and all, where people are trying to understand what is the exact force which is governing this extended to collapse kind of transition as we increase the chain backbone density, right? Now, if we put Crowder inside that, and we have two regimes now, A less than AC and A is greater than AC. A less than AC means when chain was in extended kind of regime, when there was no Crowder, right? So if we put Crowders and increase the attraction between the monomer and the Crowder, what we see is a nice again chain extended to collapse kind of behavior. And for two different valencies I am showing here, Z equal to 1 and Z equal to 3, for both of them chain was in the extended form. You can see from the RG values here when the value of A was less than AC, and all of them are going to extended to collapse kind of behavior. And we can see this is for highest value of epsilon MC, that the highest value of monomer Crowder attraction. We see that the Crowder inside the globule, this is again the density profile of the Crowder and the monomer. We can see the Crowder are more than monomers inside the globule, the profile. And hence we are showing that the collapse phase is consists of Crowder particle instead of counter ions. So this is totally governed by the Crowders, right? Then the other regime we have A greater than AC, where chain was already in the collapse form when there were no Crowders because of the Manning condensation and the thing. So we can see the value of Rg is in the collapse regime when for all these A by AC value we have taken, and we can see that again the chain goes from collapse to collapse conformation, but now both of the collapse form are again structurally different in the sense we can see the Crowder numbers are inside the globule is quite different for the two states. You can see 4.1, that is the CI phase, there are no Crowder inside, but in the CB phase we have now the Crowder inside. And to construct a phase diagram, that Rg doesn't seem to be a good parameter, so we made a plot rho bar C, that means number of Crowder particle inside within the Rg of the center of mass, and that varies nicely with the epsilon MC, and we again find the inflation point for different values of A by AC to construct a phase diagram. And this is our phase diagram looks like for the charge one. We can see for Z equal to 3, it looks similar to what we got for the neutral one, and there are three phases we are again explaining the same way. E is the extended, CCI is collapse phase due to the counter ions, and then CCB phase which is due to the Crowder phase. So here the phase space is epsilon MC, here the charge density A by AC is the charge density on the chain backbone. So what is interesting to note here is for the Z equal to 1, the counter ion valency 1, we see there are intermediate value of A by AC where there is no CCB phase, CE to CCB transition happening, right? So this kind of strip is kind of extended up to a very large epsilon MC. So why this is happening, that due to the steric effects, the number of the Crowder that can condense of the polyelectrolyte is kind of limited, and we expect if this is the reason, then the smaller Crowder should should be able to form some collapse behavior at this regime, and which was indeed the case. If we make the Crowder size the half of the monomer size, we see that the chain is now showing the Rg value in the collapse regime, and the chain is induced is indeed forming a collapse form, right? So now, like, what are the conclusions? So first is the attractive Crowder induced CG transition with Crowder acting as a bridge between the distant, or the bridge or the glue between the distant monomer. And the interesting part is this soft interaction, or the attractive Crowder can give rise to this CG transition at a very low density. So we have worked with a very low density, like 0.025 volume density, and in the where the CG transition happening due to the depletion effect requires a very huge density. I mean, in the terms of 0.6 volume fraction or sometime. So it's really nice that this kind of CG transition can be achieved by introducing attractive Crowders in the system. And the critical transition point these CG transition shows is a very strict function of monomer interactions and densities and even Crowder interactions, right? And the charged polymer also shows the same CG transition, even though even in the presence of counter ions, Crowder are able to are able to get into the globule form, right? So So what we going further, so since we have seen that the Crowder size of also playing a huge role where in making these transition happen, so it's really important to study what are the effect of the attractive Crowders. People have studied the repulsive Crowders in depletion effect and showed that the smaller the size of the Crowder, better the depletion effect, or the depletion effect can be achieved at a lower density. So we want to see what are the effect of these attractive Crowder on this CG transition. We got some preliminary results for that with the different Crowder sizes. We got that there's some non-monotonic behavior with the Crowder size. That means if we increase or decrease the Crowder size, the transition becomes easier from E to CB for a weak intrapolymer attraction, and for high intrapolymer attraction there is a monotonic kind of behavior with the sigma C. This work is still going on. We'll hope to publish it soon. Thank you.
Okay, so let us all thank Hitesh for talking about some very fundamental concepts in polymer physics. So we do have a time for a few questions.
I was just wondering what is the scaling between RG and N in your CB phase? Is it still 1/3 or is it greater
Yeah,
than
so
1/3?
it's 1/3. So that's what we have also confirmed, that we plotted with the scaling, RG scaled with the n power 1/3, and we indeed see that this is the collapse regime, that the 1/3 is kind of, for different n, they are collapsing. I mean, they are indeed in the 1/3 regime.
Yeah. So I have a couple of questions. One is the monomer and the Crowder, are they chemically same or different?
So right now, just we have a bead spring model. We have taken a spherical particle as a monomer and the same spherical particle as a Crowder particle. So chemically, they can be, I mean, different as well. So right now, like we have just taken they have the interaction, LJ interaction between them. Nothing, no chemical interaction or any other interaction. Just purely Lennard-Jones.
What about their sizes? Are they similar?
Yeah. So in the first, I showed the case neutral polymer and charge polymer. Monomer size is equal to the Crowder size. We are now varying the Crowder size in the one we are doing now.
The second question was, so when you look at your simulations data, right? What is the data that shows you the evidence of bridging in your simulations?
So first, like visualization, we visualize the data, like how each, and then we quantify the bridging as
Do
well.
you have any plot to show?
So I'll show you the thing that we quantify, how we quantify the bridging, and we see that there are indeed the bridging Crowders. Here you can see. Yeah. So what we did was sorry, here I'll show. So we find how many Crowders are there, NK we are calling them, which are in contact with K monomers simultaneously. And if like for example, we take K equal to 6 or 5, for example, so how many Crowders are there which are in contact with 5 monomers simultaneously, we are calling them as a bridging Crowder, right? And through that we kind of quantify that these bridging Crowders, and we again plot NBC, that is how many Crowders are there which are in contact with at least 6 monomers simultaneously, and we see that there is very nice increment of this NBC with epsilon MC. From there also we made a phase diagram, and this looks like...
the reason I asked this question is, see, classically when you talk of bridging, right, in polymer colloid system, you have a polymer adsorbed onto the surface of, two particles, right? That's a bridging, right?
Yes.
Is it a similar bridging that you're talking about here?
Yes, yes. So that's what. So single Crowder particle is kind of attached with the 2 different monomer, like monomer from a very distant regime.
Thanks.
Very interesting talk. I was interested in the electrostatic properties. So when you introduce the electrostatic interaction, what are the cutoff that you are using? Or you are doing any case-space summation?
Yeah, case-space summation we are doing.
And does it depend on the cutoff?
Cutoff, we have taken cutoff, I think 25 or 30.
Okay, but 25 sigma.
Sigma, yes.
That is too large, or?
Yeah, as far as I remember, we have taken this much. I forgot.
No.
We are doing in the case space, yes.
Okay, so if there are no more questions, let us call it a day and let's go for high tea. Thanks, Hitesh, once again.